Hello, this is Dr. Grande. Welcome to my video on interpreting the SPSS output for a factor analysis. I have here in SPSS, in the data editor view, fictitious data, and I have 10 variables. Item 1 all the way through item 10. So these variables represent individual questions or items on a psychometric instrument. And let's assume that we have a reason to believe that item 1, 2, 3, and 4 are related to one another. Item 5, 6, and 7 are related, and item 8, 9, and 10 are related. So we believe that in these data we would find 3 factors, that these items would load cleanly on 3 factors. So if we conduct a factor analysis, we would expect to be able to interpret the rotated component matrix and see that item 1, 2, 3, and 4 load together, item 5, 6, 7 did as well, and 8, 9, and 10 loaded together. But even if we had that as a finding, that wouldn't mean that these items are measuring the construct for which the psychometric instrument was designed. The factor analysis will tell us if the items load together, but it does not answer the question of what construct is being measured. So to conduct a factor analysis here, we're going to go to Analyze, Dimension, Reduction, then Factor. This is what the factor analysis dialog looks like by default. Over here in the left, you can see item 1 through item 10. I'm just going to hit Control A and select all of these and then move them over to the Variables list box. Under Descriptives, I'm going to add the univariate descriptives, and under Correlation Matrix, the coefficients, significance levels, the determinant, and KMO and Bartlett's test of sphericity. Click Continue. Under the Extraction item, I'm going to add the scree plot. I'm going to leave unrotated factor solution checked off, and I'm going to leave the based on eigenvalue option set at the default, which is eigenvalues greater than 1 are extracted. Click Continue. And then under Rotation, I'm going to need to determine the rotation I can use. So I'm going to start with direct oblimin, and this is an oblique rotation, and we will interpret the output and see if we're going to stick with an oblique rotation like direct oblimin or Promax, or if we can move to an orthogonal rotation like Varimax, Quartermax, or Equimax. And I'm going to leave the rotated solution checked off and click Continue. I'm not going to make any changes under Scores, and I'm not going to make any changes under Options now, but I'm going to come back and make some changes here later to show you how it changes the output. So I'm going to click OK and run this factor analysis as indicated by the parameters that were selected. And we can see we have the descriptive statistics, the correlation matrix, and a great deal of other output. But for this particular run of the factor analysis, I'm only interested in the component correlation matrix, because first I want to determine what rotation method I should be using. What I'm looking for here in this correlation matrix, you can see I have 3 factors or 3 components. I'm looking for a value here, a correlation value, that when I take the absolute value of the correlation value, it's greater than 0.32. And you can see in no case here, other than the factor correlating with itself, which of course is going to be 1, in no other case do I have a value whose absolute value exceeds 0.32. So in this case, I'm going to go back to Analyze, Dimension, Reduction, Factor, and I'm going to change the rotation to Varimax. If it was greater than 0.32, if any of those values, if the absolute value was greater than 0.32, I would stick with direct oblimin or Promax. But in this case, I'm going to move to Varimax and click Continue, and then click OK. So now to interpret the output from the factor analysis, and you can see the first table, we have descriptive statistics, and of course we have the mean and the standard deviation for all the items. And then we have the sample size, that's the analysis N, and you can see it's 200. And I use this sample size because generally 200 or above is considered acceptable, and below 200 is considered poor. So generally 200 would be the fewest number of records that you would want to analyze. Then we have a look at the correlation matrix, and you can see that we have all 10 items correlated with the 10 items, and of course diagonally we'll have all perfect correlations. So we're provided with the correlation values, and then we have the p-value here in this table below. The next table is KMO and Bartlett's test. So you see the first item is the Kaiser-Meyer-Olkin measure of sampling adequacy, and the value we have here is 0.722. In general, anything above a 0.5 is considered acceptable, although a value above a 0.6 is preferred. As far as Bartlett's test of sphericity, when we look at the p-value, here we have 0.000, which normally we would record as less than 0.001. In this case, that's the result we want. We want to have a statistically significant value for Bartlett's test of sphericity, so a value below 0.05. So next we have the communalities table, and you can see for initial all the values are 1, and we have some different values here for extraction. This extraction value tells us the proportion of variance for each variable that can be explained by the factors. So in this case, looking at these extraction values, they're very high. So these are good extraction values. Then moving down to the next table, we have total variance explained. And we can see that SPSS extracted 3 factors or components, and the cumulative percentage was 85.851. So these 3 factors explain 85% of the variance. And if we move down to the scree plot, we can see that 3 factors were above an eigenvalue of 1, and all the other potential factors were below that, so they were not extracted. Then moving down, we have the component matrix and the rotated component matrix. And this is a table that's easier to interpret when you make some changes under options in the factor analysis dialog. I'm going to go back and make those changes so that this becomes easier to read. But even without the changes I'm going to make, you can see that factor 1 has item 1 through item 4, very strong loadings. And then we have 5, 6, and 7, again very strong loadings, and 8, 9, 10. The factor loadings are high. But I'm going to move back to Analyze, Dimension Reduction, Factor. And of course it's going to retain all the properties from this analysis. So I'm just going to go into Options. I'm going to sort by size for the coefficient display format, and I'm going to suppress small coefficients. Now there are several theories about what a factor loading minimum value should be. One of the popular values is 0.3, so I'm going to use that. An absolute value below 0.3, those factor loadings will not be displayed. Click Continue and click OK. I'm going to move back down to the rotated component matrix. You can see that the factor loadings are sorted by size. So 0.981 is the strongest factor loading, so it's up top, and 0.834 is the weakest, so it's at the bottom. And you can see we have item 1, 2, 3, and 4 all load together. Item 8, 9, and 10 all load together, and then 5, 6, and 7 all load together. So by not displaying the factor loadings that are below what we would consider to be a significant loading value, and by sorting these by size, the rotated component matrix becomes easier to interpret. I hope you found this video on interpreting SPSS output for factor analysis to be helpful. As always, if you have any questions or concerns, feel free to contact me and I'll be happy to assist you.